Dr. Chaudhary, Probir Chaudhary is here. Yeah, please come. And Praveen Chaturvedi. Praveen. Yeah, please come. So without wasting much time, I'll just briefly mention about Professor Siddhartha Das. He's being our chairman. You can go that side so that, the screen will be seen. So that is the reason we made the little change in the arrangement. I'll just briefly mention about Professor Das. He is a PhD in metallurgical engineering from University of Illinois. He is a MS from metallurgical engineering from University of Illinois. And also he is a B metallurgical engineering from B College Shibpur. And his experience is huge. He is a professor, Department of Metallurgy and Minerals Engineering, Indian Institute of Technology, Kharagpur, and moved to higher administrative grade pay from in 2010. With this brief, may I just request Professor Das to take the session, please, without wasting time, so that, like we finish on time, we are coming on time. Please.
Good afternoon, everyone. Let's start with the first technical session. We have two speakers for this technical session. The first speaker is Praveen Chaturvedi. He graduated in mechanical engineering from NIT Rourkela, and he has a PGDBA from Symbiosis, Pune. He is associated with iron and steel industry for almost 3 decades in various capacities, working at Tenova for last 13 years. Prior to joining Tenova, he has served at L&T, Ispat Industries at Dolvi, and Jindal Sadid, Sohar, Oman. He is also a member of many professional societies or bodies, Indian Institute of Metals, IM Mumbai chapter live member, member of Task Force for Green Hydrogen and Energy Efficiency for the Ministry of Steel, Government of India, the Association for Iron and Steel Technology, etc. So without any further delay, I like to invite Mr. Chaturvedi to give his talk. It will be 15 minutes, sir, and then we will have 5 minutes interaction. Thank you.
Thank you, sir, for the introduction, and thank you, Steel Tech, for this wonderful session. I will start with this, the smelting, because the topic of this today's discussion is the ferroalloys as well as in the steel upstream sector. Before I'll just take a few slides just to make you aware that who we are. We are part of the Tech-In group, and we also make the steel. Basically, we are mainly into the steel sector. We make the steel around 30 million ton of steel annually we make under the name of Tenaris and Ternium. And then Tenova is a part of the same. So whatever product and technology we come into the market, we first of all, we trial and test at our own factory, our own installation. And more importantly, what nowadays everybody is looking at is as a sustainability. So yeah, we have been declared sustainability champion by the World Steel Association, where you can find the name of Tata Steel, JSW from Indian side, and then our two sister company, Tenaris and Ternium, you can see in the down, it's of course, maybe not be appearing here, but you can see the Tenaris and Ternium, we are also part of the same, and we have treated as a sustainability champions. So that is why we say that, yeah, we are the solution provider, sustainable solution provider in the sector of the metal as well as in mining. So whatever the discussion what we had in the previous session about whether to utilize the energy or whether to use for the slag or whether to go for the digitalization, all those things has been well covered under our portfolio in the sector of the metal and the mining. We are, of course, the global company located across the globe. I belong to the Indian Mumbai area, but we are Italian-based company. And to give a new mantra that has been given to us, Tenova has been inserted in between the sustainability, so it is called sustainability. So whatever we produce into the market, whatever we offer to our customer, it should be from the sustainability. We should think from the heart that it should be embedded within our concept. Basically, we are not into the blast furnace BF route. We are basically into the DRI electric arc furnace route. Then we have the reheating furnaces and downstream facilities. So these are some of the product portfolio. We are into the hydrometallurgy as well as the pyrometallurgy as well. So these are some of the brands which are associated with us. From the mining side, it is Techgraph and Dalcor. Hydrometallurgy is very important because in the previous session, Mr. Raman was mentioning about the critical mineral. Yes, that is also, we are into that, in which we are also into supply of the permanent magnet, rare earth magnet. That also one of the portfolio what we do. And lithium phosphate processing, solvent extraction, that is one of the part that includes, that is covered under our hydrometallurgy. And the topic what I am going to cover is in the pyrometallurgy, that is the smelting, whether it is for the ferroalloys or platinum group mineral, that is the recycling of those critical minerals that is already has been in the autocatalytic converters or in the PGM sector, and of course into the base metal. So regarding this, the advanced technology, we are, as I mentioned you about the hydrometallurgy, what we are, lithium battery recycling, rare earth, phosphate technology for phosphoric acid that we do, and of course we are into the beneficiation, mineral beneficiation, that is what we are also discussing at. Of course we are in the port and metal handling facility, this is the digitalization. So we are, so that is why how we treat either we have to start from the mines or from the waste. So this is how we should also think for the circular economy. So considering the waste, whether it is in the form of the slag or whether it is in the form of the dust or whether it is in the form of the scrap, that can be, yes, recycled and it can be used as a raw material. We treat the waste as a mine above the ground, and the mine, of course, you know. So yes, we do all the mineral processing, then we also into the DRI, HYL DRI, you can see in one of the top slide, that is into the gas-based DRI. Then we are into the pyrometallurgy, and then we have the downstream facilities. Of course, these are the various installations we have across the globe. So sustainability, I start with, again, with the sustainability. That includes the safety, efficiency, carbon footprint, technological transition, and future challenges. This is what the previous sessions we had a discussion on it. And how we are the readiness in terms of the flexibility is more important nowadays. Because it is not done in an overnight, it cannot be done. Rome was not built in a day, but at least one day it was built. So with the saying that whether it is for the induction furnace or whether for the BOF route or whether it is for the electric arc furnace route, whatever the secondary manufacturers also. So there are various things where we find ourselves, and this is what I was discussing with Mr. Saab, that about those things. Guha Saab, about the market, different raw materials, quality, of course, that is also deteriorating nowadays, but we have to maintain the quality not of the raw material, but for the end product. And the different energy mixes, whatever energy we are getting, we should be ready with that one. And of course, nobody is going to compromise on the productivity and the yield. When I say that, yes, we are a century-old company. We started our business in 1915. And this pyromet, we have supplied more than around 3,000 furnaces worldwide, and we have the 100 years of experience, just like Tata Steel. And when I say so, you can see our Indian presence. In 1943, we have supplied our the furnace for the ferro manganese at that time to the king of the Mysore. So it is Mysore Iron and Steel. Later on, it became Bhadravati, and now it is under the part of the SAIL, Chandrapur. Now it is in SAIL Chandpur. You can see initially the furnace looks like this, and the furnace still is working. You can see the fumes coming out of it, and I'm the person standing in front of that one. You can see on the other side of the slide in which I'm standing, and this is the furnace which is still working. The furnace supplied in 1943 in India is still working, and we are proud to be belonging to that heritage. Another furnace is for the ferro manganese. It is in Sandur. You might have heard the name of Sandur. Sandur, of course, that also belongs to the royal family. 1967, and the furnace is still working, and you can see my picture in front of that one. We supplied in 1966, and that is still working for the ferromanganese. Initially, they started for the pig iron tapping, and now they are using for the manganese or smelting. So yes, as a Tenova Pyromet, we supplied both AC furnaces and DC furnaces for ferroalloys, and for the base metal, and slag cleaning and alloy refining. That is very important topic, because from the black slag which is coming, whether from the steel melt shop or whether from the ferroalloys, that black slag, rather than using for the landfill or for the road making, we are converting that black slag into white slag, which can be used for the cement industries, just like in blast furnace slag. So that activities has already been in practice in many countries, and in India also we can use as a potential usage of that slag into white slag for the cement industries. Yeah, as I told you, this, we are into the ferrochrome, ferromanganese, silicomanganese, yes, ferronickel, ferrovanadium, silicon metal nowadays it is gaining momentum, ferrosilicon also, and these are the portfolio what we are all are into. Ferroalloys technology, yes, Mr. Sindhu was mentioning in the beginning that we should go for the bigger furnaces. Yes, you can see the installation what we have. 36 MVA, 48 MVA, 66 MVA, these are closed furnaces for the ferrochrome production. You can see 33 MVA, 45 MVA, 66 MVA, these are the closed furnaces. The advantage of the closed furnace is that we can recover the CO, carbon monoxide, and we can use it as a fuel, whether for the power generation or even for the methanol or ethanol production, which Mr. Nandi was mentioning in the beginning, in the previous slide, in the previous session, or it can be used for the preheating the raw material, so as to reduce the moisture in the reductant. Yeah, you can see 63 MVA, 75 MVA, these furnaces also working across the globe. Yes, these are our South African references. This is what Mr. Sindhu was saying, that if elsewhere people are making it, why don't we think of making the bigger furnace? Think big. This is 66 furnace in international ferrometals. So this silicon metal also we are into the one. 40 megawatt silicon furnace, that is in US. You can see the size of the furnace for the silicon metal. Yes, we are into the base metal and the platinum group. These are the various references of into the niche market if we would like to enter, like BASF and Sabana. We have supplied those furnaces, even the BHP, Olympic DAP. Of course, this is the furnace we have supplied in China. They are doing the autocatalytic recycling. Of course. Then we are also into mineral wool. The more importantly, when we are heading towards the decarbonization, making mineral wool or rock wool with the cupola furnace, this is what has been practiced in India so far. But now people are in India also, they are setting up the same submerged type of furnace, open slack bath furnaces, for making the mineral wool, which is electrically driven, not the coal driven. So that also is a trend which we can follow. Of course, one customer is in India, they are already going ahead with this mineral wool making with the electrical furnace. You can see we have many references already. POSCO has implemented, and other places we have already supplied such furnaces which are used for the mineral wool application. And coming to the digitalization, yes, furnace information system is very important, in which you can see that as we were discussing in the previous session about the skill development. Yes, getting the skilled person, nowadays it's a challenge. In our days, it used to be that by seeing and we can say that, yes, how the furnace is behaving and what is the temperature and what is the, just like doctors. Initially, doctor used to put our hand and say, and then see that what disease we are having. But now they are depending on the gauges, because on the probes, on I don't know what are sensors or probe we can say, and that helps us to measure what exactly is the body condition. Likewise, the furnace also, we are reducing the dependency on the manpower. We call it is a type of a digital foreman, no more physical foreman. This digital system that looks inside the furnace, it measures all those data, all those happening, and that it gives a corrective action. So this is what we have, furnace information system, and this is how we control. More important is the control. The control can only be possible if we are able to measure precisely in a real time, on day-to-day basis, not on day-to-day basis, second-by-second basis, just like GPS in a car. If we are able to know that where we are and how much time it will take to reach, likewise, even the furnace operation, whether it is the electric arc furnace or submerged arc furnaces, all equipped with this type of system. And it is clubbed with the machine learning, and this is how the people across the globe they are making in. This is what it can be thought in Indian context as well. So the main driver, as we know, that ore, this is what we discussed in the beginning, that is not in our control, and whatever quality is that, we have to make the gold out of it. Gold, I mean to say, not the gold as a commodity, but yeah, best of best. Reductant, availability and cost is always a challenge. Power, the cost and its limitation, that also is a big threat. And the environmental point of view, effluent and the water usage effectively, just like we have discussed in the previous session about the zero discharge. So all those factors we consider when we design our furnace. It starts with first principle. That is why I say, whether it is in India or Ukraine or Russia, Iran, whatever it may be, the chemical system remains the same. The theory what we have studied in our school days, elementary days, in organic chemistry we were told about the hydrocarbon. But unfortunately, what happened that we have forgot about the hydrogen, and so far we have been thinking only about the carbon, and carbon. Now we are thinking about the hydrogen. So it will take time for us to reach to that stage that we are talking about the hydrogen, and then how hydrogen can be used for various applications and moving away from the carbon. So we start with mass and energy balance. Electrical energy, what is going inside is electrical energy, and the raw material, what is coming out is the metal, the heat losses, the off gases. And if we are able to measure what is going inside and what is coming outside, we are able to reduce the losses, we are able to focus on the yield, that is more important. So the saying goes that if we are, money saved is the money earned. So whatever saving we can do with optimizing the furnaces, what is going, because see, every heats and every furnace is not identical. We are not here to give you the equipment, means as our philosophy. Unlike there are many Chinese furnaces which they are supplying it in a very less price. But each raw material, based on each raw material, based on the charge mix, based on the reductant chemistry composition, requirement of the output, this is how we design the furnace. More importantly, our key parameters are the electrical energy in kilowatt, of course. Oil, for the ore feeding, we have mentioned MPH, that is multiple preheater. You can see this is a closed furnace, and reductant and fluxes which are going inside. Here on one side you can see that I have mentioned dry granulation. It is no more wet granulation because it has been practiced in ages. We have the system of dry granulation of the slag, which have the effective utilization also. And then on the other side you can see the output is dry gas cleaning system. No more wet, it's dry gas cleaning system. Electrical energy and feed reductant, this is coming out. And the heat output, of course, we have to see that how we can reduce the losses. So these are some of the tools which are available with us. Dry gas scrubbing system, which is high efficiency, and it is used for the CO generation, carbon monoxide generation. Also, we have multiple preheater in which whatever gases are coming out, it is helping us to reduce increase the temperature of the raw material to around 600 degrees centigrade, successfully implemented in Kazakhstan. I'll show you the benefit out of which we have derived. And also the same thing can be also used for in the DC furnaces as well. This is the example of cast chrome. This is in Kazakhstan, big furnace, 81 MVA furnace. And you can see the temperature raw material is getting heated up to 500 to 600 by the carbon monoxide which is coming out from the closed furnace, and we are using the chemical energy, not the thermal energy. Of course, from the thermal energy, you can use it for the generation of the steam. That is the heat recovery system by installing the waste heat recovery boiler. But here I'm talking of the chemical energy, in which the hot gases. You can see on one side, I have shown the graph also, 66 MVA furnace, no preheating versus the preheating. What are the incremental benefits are there? So you are able to reduce the electrical energy, 500 kilowatt hour per ton. Then you are able to also reduce the volatile matter which are present in the reductant. And the furnace operation is quite stable. Throughput also increases, ore throughput also increases. So these are the things which has been implemented, can be thought of in Indian context, but it is not possible in the open or semi-closed furnace. And this is what Mr. Nandi was mentioning, that if we are having the closed furnaces, we can move in this direction. So this is about the ferrochrome furnace. Then the fine ore preheating system that can also be applied for the any DC furnaces also. We say multiple preheater, that rather than handling, we divide all the raw materials in various bins, and the gases, the CO gases goes into all the bins, and it preheats them, reduce the moisture content. And you can see how the system works. Of course, before we are not putting the fumes with the dust into the preheating section. First of all, we remove the dust. We capture only the carbon monoxide. Nowadays, we are working with one company. We are giving them the carbon monoxide to them, and they will add the hydrogen and make the hydrocarbon, which are used for jet fuels and other methanol, ethanol making. So that exercise is also in practice, because the CO we are treating as a fuel. This hot gas filtering, also the same system. It helps us to reduce the water requirement, and it also helps for the any carbon monoxide gas explosion. Dust handling is very less. This is the scheme of our hot gas filtering. I'm just moving to the another that also helps to reduce the carbon dioxide emission system. These are the furnace gas cleaning system. Yes, this is about the wet and the slag granulation system, wet or dry. We can provide both, but they have both have these certain advantages and disadvantages. Wet, it needs water, of course, but risk is that there is some chances of the explosion, and we need the water treatment facility. On the other hand, the dry granulation, we don't need any water. It's very easy, very simple. And not simple, of course, technology we have, but it requires very less very less area footprint. Yes, some operator training is required, and this is a better way how we can go with the dry granulation system. Of course, for the wet, we are already into the wet. We have our Delcor division, which does the solid and liquid separation. But if we focus on the dry forced air granulation system, you see the slag which is coming, we put into the granules forms, and those granules that can be used for various applications. No need of crushing and material handling and a lot of the pot carriers and those things. Of course, this is the thermal energy which is coming from the furnace, can be recovered and through the waste heat recovery boiler, and the steam can be utilized for various applications. That is also one of the technology what we have. And there are various applications of the steam. And of course, that also helps to reduce the carbon footprint. Yes, we have our own electrode column design, our own proprietary column, electrode column, for bottom as well as for the upper. This is our proprietary atom which we supply. More importantly now is the autoform, the furnace controller, how we can control the furnaces. So these are the controllers, digital things which helps to read the furnace, what is happening inside the furnace, and then if we are able to measure all those data, we are able to control the factors. So these are the benefit. You can see it helps us to reduce the electrical energy, electrode consumptions, because this is the total furnace controller, and that has been already in practice in SAIL Chandpur. Of course, SAIL Chandpur, they have the 1943 very small the ferro manganese furnace that is also operating, and in SAIL Chandpur we have 45 MVA, the largest ferro manganese furnace, Chandpur ferroalloys plant, supplied by us, Tenova, that is also working, and it has all those autoform features already integrated. No need of any human or manpower intervention, and they are able to make the system work. Yes, there are various add-on systems which are associated with this, our iTap for the tapping, also for the ladle management. All those things, those features are already available, and those things can be recorded and can be remotely controlled also. These are the virtual, and of course these are all clubbed with our digital packages. Then there are some robotics application, no need of human to go near to the furnace, also helps us to reduce any chances of the accident, or very helpful for the safety point of view. Of course, these are the things you can see. We have also the robotic system which helps to do the welding of the steel casing and anything if required, rather than any person going there. We have various sensors which helps to measure the total things. So this digital package can also helps to see what are the plant progress. We can see remotely. You can see this can be known with various colors. This is installation of the equipment from the planning stage. Of course, these are some of the system which we can replace the blast furnace. If we want to make the steel, which is what I was discussing with Mr. Somnath Guhaji, that yes, if you are having induction furnace, you need not cry. You can still make the better quality of the steel. How you can address the phosphorus? The system is already in implementation, thanks to Mr. Guhaji. So one thing is to go without blast furnace, one is, without using the coke oven. One is through induction furnace, another one is the submerged arc furnace can also be used for melting those rotary kiln DRI into the iron, and this is what we are supplying. Of course, this can be implemented to the gas-based DRI as well as to the rotary kiln DRI also. We call it open slag bath furnace. It's just like submerged arc furnace, but works in a brush arc mode, not in a submerged arc, because our aim is to reduce the, to melt that solid DRI, and another one is to remove the impurities, because it has got the slagging facility. So it helps us to reduce the phosphorus, because there is a slagging facility, and also to make the proper. And coming to the steel, yes, Tata Steel has given us the opportunity to put our largest electric arc furnace in Port Talbot, and this is what we are going. This helps to reduce the carbon footprint, and this is the picture of last year in which Tata Steel has given us that job. And yes, in the end, sustainability, it should come from the heart. That is what we believe. That is why I put it. Thank you.
Thank you very much, Mr. Chaturvedi. Towards the end of the session, we will take questions for both of you. So our next speaker is Dr. Praveen Chaudhary. Dr. Chaudhary is the president of Education and Consulting LLC. He is a metallurgical engineer from IIT Kharagpur with a PhD in engineering from University of California at Irvine. His current technical focus is on the application of fundamental metallurgical principles in advanced manufacturing to develop, test, inspect, and qualify engineered products for all industries. He has more than 30 years of experience in materials, processing, and product development, serving aerospace, defense, automotive, medical, and other commercial industries. Dr. Chaudhary began his professional career at National Center for Metalworking Technology, where he developed and managed several large programs for the US Navy Manufacturing Technology Program. He also served as the chief metallurgist at General Dynamics. He has published more than 50 technical articles in journals and proceedings, more than 100 technical bulletins and reports, and made numerous technical presentations. Currently, he is providing education, training, and technical support to metallic and materials developer, manufacturer, and end users of resulting engineered components and systems. So I request Dr. Chaudhary to give his presentation.
Thank you very much for having me here today. And I was lucky to be here in India for a different reason, but then I was asked by, inspired by Deepak Vobing, my good friend from IIT Kharagpur, and also Dr. J.K. Jayanta Chatterjee and Pritish Jain. So I'm privileged, I feel privileged that I'm here today and in front of you talking to you about something about what I learned. Okay, so I'm going to give you a little outline of what my presentation is going to be. So I'm going to talk about transition from Industry 2.0 to Industry 5.0. This is what I've been talking about, but not in the same perspective as I would be doing, but I was going to be giving you more structure to that, I should say. So there are archaeometallurgical evidence of iron making. Iron making started actually in India, in Gupta dynasty, about turn of this millennium, which is around 200 BC to 100 AD, around that time. And so, but anyway, you'll see that. So then we are involved into what do we have today, current and modern steel making. We're going to talk about more of the sustainable steel making, as some of you have been talking about in this forum today. So I just wanted to talk about a little bit of the future of what is going to happen in steel making. And my perspective is slightly different because I was always worked for a product company that actually produced systems, produced products, components, aircraft, all kinds of things that you can think of. And from that point of view, what is my interest is in how are people making steel now today, and how we actually have been evolving. So I'm going to talk a little bit about that. So I'm going to also talk about metal additive manufacturing and advancements in metal additive manufacturing, how we can actually implement those into making steel products as well as steel raw material. So adaptation of metal AM technologies and direct reduction of iron and steel, how is that going to work for steel production? And of course, we'll talk about the ferroalloys and things like that a little bit. So feasibility and maturity required technologies, because I am actually a metallurgical engineer, like many of you are here, core metallurgist. So I know what is the most, what are the new technologies that we need. So you will talk about, I mean, I can talk about a lot of different things, what is happening with the digital world today. How did this all happen? But that's besides the point right now. So then I'll give you a little summary. So let's take a look at what is transition to industry 5.0, because you really need to have economic, energy efficient, agile, and environmentally beneficial products. And those Industry 2.0 was the Industrial Revolution. At that point, we needed to actually have a lot of material, a lot of raw materials to make things. So these are all experience-based legacy systems, very high volume production, and in the process, we developed a vast amount of knowledge of metallurgical engineering, steel making, and all of those things, beneficiation, everything that we talked about today. And so those are the bases, and they are still needed today. And then it comes to the Industry 3.0, where we started doing an analysis-based production system, not the experience-based alone. So experience built over analysis. And then you actually integrated all the advanced technology bases and knowledge bases together to basically get into Industry 3.0. 4.0 is now, it becomes performance-based system, where you need low volume production, integrated supply chain, etc. So at the beginning of the Industrial Revolution, we needed a lot of material, product, quantity mattered. Now, it's actually quality that matters slowly, that we're going from the quantity matters to the quality matters. And that's why finally the Industry 5.0 is what is going to give you the sustainability, which is the manufacturing to scale. When I need what I need, I make it to that scale. I don't want to have excess material. I don't have to have shortage of material. So I need, how do we do that? And that's what allows us to become more sustainable. So just in time, energy efficient, all have been, everything has been talked about before. So also the environmentally sustainable. So all of these needs to be backed by something. Manufacturing enterprises. I see a lot of you who are from industry, and that they're here. That's a very positive sign that we can put together our collective technological advances, use the scientific research and development in the industry as well as in the academia, and then use all of this together. And I think it is an opportunity here, the steel tech, to be able to do that, can bring everything together. And that's what the essence of it. This is what I'm learning here right now. So, I mean, I can talk about very quickly some of the things. What are the modern advances in manufacturing Industry 3.0, which is this process model simulation, all the integration of ERP, MRP processes that we do, but over software. So majority of the things are actually software-based, right? All of the Industry 3.0 are software-based. So automation, robotics, all of those are software-based. Then we have more advances in manufacturing industry, which is related through 3D CAD modeling. So we needed 3D CAD. So all the digitization that we're talking about here in pyrometallurgy, in all kinds of steel making things, that can be actually utilized in the digital world. And that's where we'll be able to communicate with each other. We design product, we don't know how to manufacture it. And then so we need to combine them. So 3D CAD modeling became one of the stepping stones for that. So we had a 3D model. I can ask the 3D model to be produced, and producer will say, okay, I'm going to make it this way. So somebody's going to say, okay, I need this material. So all of those has to be digitized completely. So that completes the digitization of the manufacturing, which is very difficult thing to do, but it has to be looked at that way. So a lot of this process modeling and that we're talking about, so you have sensors that senses things, whatever the amount of carbon dioxide you're getting to your flue. And things like that, you can actually, from those, you learn so much, and then you use that to simulate the process and finally refine the process on the fly. Okay, so those are the things that you can do. So you also can integrate machine learning, artificial intelligence, all of these things can come together if we have the proper digitization of all of the aspects of manufacturing process. So metal additive manufacturing, this is what I've been working on nowadays. It wasn't there for very long ago. So I'm going to talk about metal additive manufacturing a little bit and see how we can actually take advantage of some of the things that we're learning from additive manufacturing to enhance what we can do in manufacturing today. So advancement in metal AM is all known. There are lots of advantages. I'm not going to go read them because they're direct manufacturing process from a 3D CAD model. Give me a CAD model, give me the material, give me the energy. I can make a product directly from anything. It could be an ore. I can start from an ore and finish with the product. I can mix different kinds of ores. I can do all the calculations to figure out how much of what ore I can have, and I can actually do the reduction in an additive manufacturing process machine and with hydrogen and actually get a product which is finished product. We don't have to go through all of that. But anyway, I'm going to get to that in a little bit. It's a lot of reduced lead time of manufacturing. These days, it takes a long time to get the material itself. And those things have been solved by doing additive manufacturing because you can do any small. So scaling down was a problem because once we have the blast furnace, we scaled up, scaled up, scaled up. And then in the US, what happens is they have so much scrap. They can use all electrical arc furnace now and then make all of the steel they need because they're not making a huge things anymore. They are making smaller things and they are basically sustaining the manufacturing base. That's all they're doing. So therefore, their demand for steel is not there. And look at China, what they did 10 years ago, about 10, 12 years ago. They purchased all of the scrap from America. And they actually started using electric arc furnace, and they have built up many different ways, conventional manufacturing as well as electric arc furnace to melt scrap. So, so that's, you can actually see the whole story, how it's going, evolving. But anyway, let's get back to the industry 4.0 and 5.0, which is it's the enabling the digital transformation of manufacturing, completely digital. So we have a lot to do still in every aspect of steel making, every aspect of manufacturing products. Allow digital twin development, the performance-based qualification, which is different thing right now in this process here, because I am involved in a lot of the qualification process and figuring out how to qualify products for critical applications. And that's where these kinds of things come on, but it will happen later on. Also enable hardware-based agile manufacturing. So additive manufacturing is the only thing which actually makes you agile through a hardware, not a software. It's not an ERP, or any of those that you do computer simulation to figure out how to lay out your. So all of those are developed was all software, but hardware, additive manufacturing is one which you could actually make a part, ask for a part in the morning, and next day morning you will have a part. It could be even from a raw material as farther as the ore. So anyway, those kinds of possibilities, so we'll talk about that. So there is a lot of opportunities for innovation, and I know that their innovations in India is amazing, actually. You can actually see all of those things all over the places. So I think this is an opportunity for the Indian manufacturing industry here. So let's talk about this very quickly. First iron part, first large iron part was made in Gupta dynasty about, talked about already, BC 2nd or AD 4th century. And these are the Delhi iron pillar. You can see the picture of the iron pillar. There are cannons. These are actually made by additive manufacturing. What they did do, they actually put ore and flux together in a 20-kilogram ball. They heated it up. They didn't know how to melt. There was no blast furnace then. There was nothing. And they were able to hammer together these 20-kilogram balls of heated powders of ore and flux and that. And the flux spilled out, and they actually made this layer-by-layer structure, which is produced by additive manufacturing. So if you think about additive manufacturing, it was actually pretty much used first here. So anyway, so let's take a look at what's the growing demand of steel. Growing demand of steel is pretty large, and which is not just in India, but all over the world. It's a global. So this is a comparative scale, so a scale of 500. So if we need something about 500 in 2035, today is 300 that we produce. So it's basically a scale. So if you look at it, steel has the largest demand for all metals. So steel is still the most important material, and actual aluminum is growing very fast. So aluminum is the fastest, steel is the largest or dominant in the demand space. So let's take a look at global steel demand now. If you divide it by companies, a lot of this data came from some of the Steel 2025 report. And they was comparing 2014 and 2024. If you look at India's demand was 4.9% in 2024. Now it's 8.5, almost double, more than doubled, right? And if you look at some of the other countries, they also have some increase, but not as much as in India comparatively. So that's the reason where it comes from, how much we need. These are the finished products, okay? Now if you look at this crude steel production in different countries, or in 2014 and 2024, in 10 years' time, India's 5.2%, and then now it's 7.9%. It's increased, but not as much as the demand itself. So I think there is an opportunity. That's what you see, and that's another came out in another report. Anyway, so I'm not going to get into that because this is all you very well know. The various methods of making steel from the iron ore and use of different kinds of processes. So, but the point I'm trying to make is these are all high energy consuming processes, extremely polluting. Carbon footprint, it causes about 11% of the total, 8% is coming from steel making. So economic only when you make a whole lot. That's why you have to put 5,000 tons of pig iron in your blast furnace. You don't make 200 pounds or 500 pounds. So you cannot, it's very hard to scale down. So the scaling is important, but scaling down is a future demand that you're going to see as we go to Industry 5.0. So this is the now whatever electric arc furnace, and the thing to look at electric arc furnace became so important because people were able to do the recycle the scrap, and that's one of the reasons why in the U.S. now recycling or using electric arc furnace to use the scrap is much higher, and you'll see that in a minute. So, sorry. Look at the global trend, net zero steel industry, which means that I'm not going to produce any, the carbon footprint is zero, right? There's no, okay. So China leads the global steel production by a large margin, 1 billion metric ton versus second place, India is about 149.50. So if you look at that, there is a huge disparity. China makes more steel than all of the other countries together, right? And then what is happening is that, look at China is declining because they are not going to need, they have collected, they become, and US did that much earlier than that, before China. And US became scrap rich. And some of the scrap went to China, some of it went to other countries, they actually used that. But anyway, the point is that the next 20 to 30 years, you can see, look at India has the largest rate of increase in steel production in next 20 to 30 years, which is what you all have been talking about now. How do I step up, basically, right? There's an opportunity there. Now, if you look at all of those, where are we stepping up? And where we need to go is kind of an idea that you get here. From the conventional blast furnace, oxygen furnace, basic oxygen furnace, to making steel, and all of that is going to change. And you are going to go into another area, which is the hydrogen economy. Hydrogen economy is coming. No matter what you say today, it's going to come. And you can see every country is preparing for it. Nowadays, I also heard that some people are asking for the green steel in their requirement. So those things are going to happen, and there is a good reason for it. Hydrogen is the best reducer in the world. That's the highest energy capabilities in hydrogen. And there are lots of other material, other gases that could be used too. So anyway, so if you look at all of those, in all of those, only India has the very high rate at which it's going up, but you can see the blue line, which is basically the direct reduction of iron. And if you look at all of those other countries, like South Korea is pretty good, but they're stable. They're very stable, but they are already making pretty, so by 2050, everybody's going to go to the kind of net zero steel industry. So anyway, so this is what Switzerland is doing right now. Switzerland has this blast furnace. They use only hydrogen instead of any fuel. And they have actually shown that it can be done in a very large scale. But it is hard to scale it down. What if I need only 200 tons? I'm now at 2 tons or something like 1 ton. So those are the things that are happening in the US now, but those are the problems that they have to solve. So there are future opportunities, there are near-term opportunities and long-term opportunities. So large-scale production of steel is going to go towards hydrogen direct reduction. Development of ferroalloys by hydrogen direct reduction. I heard about ferroalloy production here this morning, and I learned a lot of different things that people are thinking about. They're all thinking all in the right direction. And everybody's had talked about different separate things, but they all combine together to be a nice view of what is happening with the ferroalloy production. And that's why we need to get it, like somebody said, bigger is not better, smarter is better. And that's what we need to think about. But anyway, so agile manufacturing of discrete parts, scaling down, all of those things are important. And I'm not going to get into all of the details. But then the point is the development and application of advanced metal additive manufacturing innovations for direct reduction of mineral oxide ores is very, very important, I thought. And then it could be a thing that you need to look into. So steel and metal parts, functional but not non-critical parts, can be made. You can actually bypass casting altogether. You can make the part real from the ore to the finished product. I don't see any problem. And we'll show you how that. So feedstock, you can make this feedstock as a secondary part making. So forgings for critical parts. You can actually make a preform and then forge it to make a finished product. So you bypass all of the extraction on that. Other intermediate products, so then you have ferroalloys, and I've listed them, some of them, but you all know that because so what is happening is the current additive manufacturing, metal additive manufacturing has the biggest problem is the raw material. So what they do, conventionally produce the material, steel, iron, whatever, everything you produce by conventional extraction process. and then you add energy and cost to make a powder or a wire. Your raw material, starting material in additive manufacturing is either a powder or a wire, majority of them. There are lots of different other ones too. So you start with the mineral ore, extract, purify, alloy, shaping into a form, wire, bars, billets, and all of that stuff. And then you do the wire drawing to make the wire that is going to make additive manufacturing raw material. So it becomes very expensive. Okay? And then otherwise, you also now make a product, then you remelt it, then you make a powder, and then use that powder to do the 3D printing or additive manufacturing. But that's not sustainable. That's why it hasn't happened in steel very much. It only works for very expensive materials, not for the steel. So that's why. So if you want to do it in steel, you got to additively manufacture from just the mineral ore directly. But then that's going to be a small scale first. So large scale, what do? We can do a lot of other things. So in this case, what you would have, a mineral ore, and beneficiation becomes very important. How do you enrich the minerals to exactly what you need? And then you can use additive manufacturing, and then you do a powder bed fusion. I don't know if you are familiar with that. If you don't, I have a bunch of supplemental slides that I can actually explain to you how it works. It's basically a powder bed. It's basically a fluidized bed. Nothing else, nothing different, nothing much different. So you have a very thin layer, a few microns, 70, 60 micron layer of iron ore, and then you pass hydrogen gas, and with the laser you heat it, so you get with the hydrogen, becomes a fuel as well as a reducer. And so all you get is water vapor in the end, and you can recycle the gas also, and so on. And then you can actually make the part directly from the ore. So you don't have to go through this extraction process. But then beneficiation becomes very important. How do you enrich it to a level where you can actually use it directly into the machine? So anyway, so you can do a binder jet process. Basically, binder jet process is nothing but pretty much like a powder metallurgy product. So you make the shape with the iron ore and binders and things like that. You burn off the binder and then reduce the ores into the raw material or the metal, which could be alloys too. You can alloy at the same time. Then there are also other processes like wire. Through wire, you could actually use a cored wire, put the ores in. In fact, I have actually got a patent on making HEA, high entropy alloy, using stainless steel wire and putting oxides through it, and then actually do electrical welding, basically. So you can actually do those kinds of things. So there are a lot of different small things that you can do to make a difference. Oops. But all of this is because why is it feasible? That's the very thermodynamical, metallurgical thermodynamics that. So anyway, I'm going over time. So I want to say is that two things. Since 1977, people have been doing research on the thermogravimetric research and figuring out what happens with hydrogen. So you can actually see some of the numbers. Activation energy in 1977 with 200 micron, in 2005 about 100 micron. All of the different kinds of powders they actually did with, you can see the lowest activation energy is with hydrogen. And now at the bottom you can actually see the kinetics of the reaction, which tells you the reaction rate. So in additive manufacturing, it's very fast. It's just a fraction of a second it takes to do the reaction. And you can do that if you go to a high enough temperature, and I will show you in a minute, because all of the fluidized bed, they experimented up to 900 degrees Celsius. And you can actually see even then the kinetic or the K value, natural log of K, is about 10 to 100 times bigger with hydrogen alone. Hydrogen CO, you can do that, and only CO, then you have a different number. So you can actually see the scientific merit of this. So what I did is basically I took all those data and put them in a chart and say, okay, how long is it going to take? If I go in additive manufacturing, you can actually bring it up to 1400 degrees Celsius. This is in Kelvin. So your temperature is going to be very high, and iron oxide would have two different stages of your reduction, and all of that could be accomplished very quickly within less than a second. if you go to this temperature. So if you do that, the R square is fantastic. Actually, it's almost 1, right? Which means the correlation is such that you can actually confidently say that I can do this reaction, make this reaction happen within less than a second. So, those are the feasibilities are there already. So this is with the AM additive action with laser beams. But then there are electron beams, there are a lot of other processes too. So if you look at some of what is happening out, there is an exponential growth of R&D and publications. Hydrogen reduction of iron ore. Look at the publication numbers, they're exponentially growing. And a lot of these are coming from China. And then also there is also scalable hydrogen production from ammonia cracking. You can use not a nitrogen-hydrogen mixture. You can actually use ammonia gas, crack it in the chamber, and then get nitrogen and hydrogen separated out, and then you get the hydrogen that does all the reduction for you. So, and in fact, ammonia is being used for gas turbine engines now to make power instead of methane gas, and natural gas. They will be ammonia because that's got a tremendous amount of energy value. So those kinds of things are happening, and then, well, I just saw the other day in the newspaper, there was an article about what is happening in India, and there was a big tank of ammonia. I have that slide in here, but I can show you. I'm running out of time here. But the point is, though, the hydrogen economy is coming. Everybody's making green hydrogen. And solar energy is amazing. You can use the solar energy. So what is going to happen? If 2% of, there was a time when in the US they said there's 2% of all the cars became electrical, then there's not enough power plants to produce enough electricity to power all those cars. That's going to happen to India too. Because just think about that. If we don't make the power plants bigger and a lot more power produced, you will have problem. But then you have solar energy. So you can actually do solar and hydrolysis and all of those different green hydrogen production and use ammonia also. So there's a lot of opportunities out there. It's just we'd have to figure out collectively with all of us together that we can do something great which will meet the demand for steel in India. So anyway, this is just a summary of all of that, what I said already. So if you have any questions, I'll be happy to answer.
Thank you, Dr. Chaudhary.
Yeah, thank you.
We may take a couple of quick questions from the floor for both speakers before we break for lunch.
Sure, go ahead. You need a microphone?
Oh, he is bringing.
So there are two quick, I think, observations, not the questions. First one is, in your graph, I see that South Korea Korea is going to grow virtually in steel. But that looks like it's not going to happen.
No, it's a level.
In fact, we are expecting that this would actually come down like Japan.
It may come down, but they're going towards already electric arc furnace and scrap. So the problem is that what we have is I think India did not produce enough steel when there was time to develop all that. We did not, we didn't have lots of bridges, lots of steels. Use of steel was actually quite limited in 50 years ago. And therefore what happened, we did not produce scraps 30 years later, so I don't have a scrap to remelt, right? So I have to use the blast furnace. There's no other choice.
Okay, and the second observation, not observation, little question is, when you look at the options of hydrogen, okay, it's all about economics.
Yeah, definitely.
So according to you, which is running faster as a technology option? Is it ammonia? Is it, we produce green hydrogen? Or is it something else that the world is still exploring?
Well, the world is really exploring right now. I know there are a lot of people who are bringing a green hydrogen right now. All of the green hydrogen, in fact, very near to my house, actually, they have just started a new green hydrogen production plant. And they're doing basically hydrolysis of water. Okay. Now, where is the power going to come to do that, right? So they're utilizing solar to get the power to do the hydrolysis. And so therefore, of course, they don't use purely solar, but it's mixed with that. Only 30% of the power comes from the solar. So therefore, those are the ways to do it. You have to combine some renewable energy sources and be able to utilize water to get hydrogen gas. So, but I think ammonia is probably going to catch up much quicker, early, but that's my feeling. I don't know.
Thank you.
Okay, one last question from there.
Yes.
Yes,
Yes,
please.
yes, yes. Absolutely.
Yesterday I saw in paper that from a breakthrough technology has been made for atomic energy production to thorium route, not uranium. Thorium can replace uranium. So do you think that it will be sustainable, means cost-wise sustainable? In that case, it is a great achievement. If through thorium you can make electrical energy.
I'm not aware of that, first of all. The thing is that basically...
There's a lot of discussion taking place that after Russia, India has achieved that kind of thorium to power, atomic power.
Okay. So what is the green hydrogen production method that you said?
Once you are able to produce electricity at low cost in a renewable way, that will solve all the problems, whether it's hydrogen, electrolysis, whatever it may be. Most important thing is getting renewable energy at the lowest cost, and that thorium can be a good replacement.
Oh, is that nuclear energy? That's what we're talking about, right? Okay. Again, that's a question of preference for different countries at different point, right? And I think India makes what, 20% of its electricity from nuclear? Even less than that, right? Less than that. So we don't really make a whole lot. But then there is also implication of safety and whatever. How much can you do? Can we actually protect the lives from radiations if I went to nuclear reactors to produce steel? Because there are materials that are needed to be able to protect from the nuclear radiation. So your waste product, what are you going to do with this waste product?
And thorium technology in this.
Okay, we can take this question and discussion during the lunch hours.
Yeah, that would be a good idea.
We
I
are
don't really
running
know.
late. We thank both speakers for giving wonderful presentation. Thank you so much.
Thank you. Thank you. Oh, thank you. Appreciate it. Thank you. I hope.
Thank you very much, both Dr. Chaudhary, Praveen, and of course, Professor Siddhartha Das for having this technical session one very lively and good. So we'll break for lunch, and before we break, can you just take a photo for this session? And also later on Kunal to help us. Here by 2:30. I request you to assemble here by 2:30. Please go for break for lunch. Yeah. And the next session will make this one. Kunal, we'll just make the arrangement for the next session.